Part 2 of Unit 11 is about the equilibrium constant, abbreviated K. Alright, let's derive the equilibrium constant here. We're going to look back at the equation from video 11.1, the balanced equation. We had N2O4 decomposing into two NO2s. And the reverse of that reaction is 2 NO2 combining to make N2O4. Once that reaction has reached equilibrium, the forward and reverse reactions are happening at the same rate. The rate laws for these two reactions in the forward direction are rate forward is equal to the rate constant forward times the concentration of N2O4. Our rate law for the reverse reaction, our rate reverse, is equal to the rate constant reverse times NO2 squared, or to the second order. Those are the rate laws for the forward and reverse reactions. We can rearrange these because we know that at equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. So rate forward is equal to rate in the reverse reaction. We can set these two things equal to each other. So setting those equal to each other, I get rate constant forward times the concentration of that reactant, N2O4, is equal to the rate constant reverse times the concentration of those reactants squared. I'm going to rearrange this so that I have the rate constants on the same side of the equation. So I'm going to divide the reverse constant over. I get Kf over Kr. I'm going to take this term and move it to the other side as well. So I'm going to get the products of the original reaction, NO2 squared, divided by the concentration of N2O4. This right here is called an equilibrium expression. We've taken the product concentrations divided by the reactant concentrations, and this, the ratio of the rate constants, is simplified to capital K. It's called the equilibrium constant. K is a specific value for a reaction that's temperature dependent. So when you're given a balanced reaction, so let's just assume this is our general form for the reaction. The lowercase letters are the coefficients, capital letters are the products and reactants. The equilibrium constant is the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Oops, that's what I meant to do. So this is called an equilibrium expression. It's how you solve for the equilibrium constant. The important thing to remember is it's always products over reactants. Some notes about the equilibrium constant. There's several different types of equilibrium constants that are all calculated the same way, products over reactants. K with the subscript of C is just equilibrium constant for concentration. KEQ just stands for equilibrium. KP is pressure. Ka is acid. Kb is base. Ksp is solubility product. And yes, we're going to be talking about all of these. Only gas phase and aqueous solution species are included in the equilibrium expression, so you need to make sure you leave out solids and liquids. Only include gases and aqueous solutions in equilibrium expressions. Now earlier when I was writing the equilibrium expression, I was using brackets to indicate molarity. There's a special way to write the equilibrium expression for gas phase reactions because the AP graders are kind of picky. So for gas phase reactions, when you're using pressures instead of molarities, you're going to write it like this. Kp Instead of using brackets, you're going to use parentheses. So you're still going to have the products on top. You're going to put a capital P for the pressure of that product raised to the coefficient times the pressure of the other product raised to the coefficient divided by the pressure of the reactant raised to a coefficient times the pressure of the other reactant raised to a coefficient. So for Kp, when you're using pressures, you need to make sure when you write your general equilibrium expression, you use parentheses and the capital P instead of brackets that indicate molarity. A large value of the equilibrium constant, so much greater than 1, indicates that products are favored. So that means that when a mixture is at equilibrium, there's a lot more products than there are reactants. A small value of K, much less than 1, so like a big scientific notation negative exponent, indicates that reactants are favored. So there's more reactants than products in an equilibrium mixture. The most important thing about the equilibrium constant is there are no units. Everything divides out. Your question for this section: at equilibrium, 0.5 molar lead nitrate, 0.9 molar potassium iodide, 1.5 molar potassium nitrate, and 2.5 grams of solid lead iodide are present. Write the equilibrium expression and calculate the value of the equilibrium constant K.